The second part of this chapter is about reaching chemical equilibrium. When do we reach chemical equilibrium? We reach chemical equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. The value of Kc depends on if we have more products than reactants. In that time Kc is going to have a very large value, or if we have more reactants than products. In that case, we're going to have a very small value of Kc. When we have a very large value of Kc, if we look at the math equation, if this number is really large and these are tiny, the value of Kc is going to be large. And this only means that when we have the reaction, at equilibrium we'll have a larger concentration of products and a very small concentration of reactants. When Kc is really small, that means that this number over here is tiny and this one over here is large. And if we look at what it means that at equilibrium the concentration of the products is really small compared to the concentration of the reactants. So as a summary, if Kc is close to 1, the concentration of the reactants and the products in equilibrium, they are similar. If it's small, the equilibrium favors the reactants, and if it's large, the equilibrium favors the products. So given these two equations and we have the Kc values, let's see which one gets favor. Well, in this case it's really large, so the products are favored in this reaction, this equilibrium, and this one is really small, has a negative exponent, so the reactants are favored in this equilibrium. The last part that we're going to learn in this chapter is about Le Châtelier principle. Le Châtelier principle states that when a system is in equilibrium, if we disturb this equilibrium, the system is going to try to reach the equilibrium again by favoring either the reverse or the forward reaction. Let's take a look of what this means. Let's say that we have this equilibrium over here. We can stress this by adding more of this. If we add more hydrogen gas or iodine gas, what is going to happen? The system is going to try to do the opposite by favor the reaction that gets rid of it, which is the forward reaction. Now, if we remove either of these, if we remove hydrogen or iodine, then the system is going to try to reach equilibrium again by doing the opposite, meaning that it will favor the reverse reaction. So if we add hydrogen or iodine, we're favoring the forward. If we add more of Hi, we will favor the reverse. Again, we can do removing the reactants. If we remove any of these, so the equilibrium will favor the reaction that makes more of it, which is the reverse. If we remove some of these, the equilibrium will favor the forward reaction because it's the one that makes more of it. So let's take a look of this equation over here and see what happens if we disturb our equilibrium. So if we add some of these, what is going to happen? The system is going to try to get rid of it by favoring the reaction that gets rid of it, which is the reverse. If we remove NH3, we remove this. So what is going to happen? The system is going to try to make more by favoring the forward reaction. And if we add a catalyst, well, no change, because catalysts don't do anything to change the concentrations of the equilibrium. Now, we have the following equation, and let's see what happens if we add an O. If we add some NO, the system is going to try to get rid of it by favoring the reverse reaction. If we remove NO2, then the system is going to try to make more by favoring the reaction that makes more, which is the reverse reaction.